next up, we have What's Next with the A2FPGA from Ed Anuff and Josh Norrid. Last year, they introduced the A2FPGA to us. They're back again this year to talk about what the latest updates are, some cool features, and the roadmap for what's ahead.
Great to be back. We last year did bring you all up to date on what A2FPGA was all about. Really, sort of what we were, what our goals were in terms of bringing a modern FPGA into the Apple II as a card that could be used for delivering, multiple pieces of functionality, Mockingboard, Super Serial, and of course our favorite, which was the SuperSprite. So we caught you up on all of that stuff, and hopefully people have seen that. This time around, what we wanted to do was jump in a little bit of a shop talk, some of the things that we fixed, kind of where we're going with it, and hopefully have enough time for questions. So that's basically the plan for today. We do have some slides here, and I'm going to put those up. So a couple of things new from A2FPGA, some more exciting than others, but actually I think all of them turning out to be things that people were very interested in. And so we'll jump into each one of those. I think the What's Next section is pretty interesting, but we're pretty proud of some of the other pieces, and we'll get into that in a minute. So Super Serial, we had a lot of people asking about that. Of course, Josh, you're a big user of that. You want to jump in and talk about what that was all about?
Yeah, sure. So with the original design of the A2N20, Ed had managed to put together a faithful implementation of the Apple II Super Serial card. But after using it with ADT Pro and specifically vDrive, one of the things that we noticed was that we were still limited to the 19200 BPS that basically is represented on the actual dip switches of the Super Serial card. And then we learned, this has all been a wonderful process of learning. We learned about the undocumented mode of the 6551, where if you put a value of 10 hex into a specific register of the 6551, you can actually crank that up to 115 BPS as long as interrupts are disabled. This greatly enhances the speed of ADT Pro when used over the Apple II's Super Serial card. And so it's really nice and convenient to be able to have ADT Pro running on a Super Serial card inside of a real Apple II and connect you with no dongles or adapters or 9 to 25 pin adapters or anything, and just go USB-C to USB. Into a modern device. So that is now working. We had a couple of compatibility issues with that, and we patched a couple of different times and then added that into our a bundle of firmware updates that we published Christmas of last year. So ADT Pro and vDrive now run at the best possible speed over serial lines with the new Super Serial card implementation, and that is on That is on slot number 2, if you choose to enable it.
Cool. So let's talk about MB Audit. So this is one of the ones that we knew when we were building the card, and I'd say it was probably brought to our attention pretty late in the game that MB Audit was not passing. But we figured it would be something simple. It later became more important because obviously the MB Audit pieces are part of how Total Replay figures out whether speech is capable and other stuff. And so this was something that was percolating up, and at first, again, we thought it was specifically some compatibility issues around 6522, within it, certain register handling and pieces like that were brought to our attention. But what actually turned out to be more of a real issue that we needed to fix was we got a lot of these things fixed, but we were starting to see that we were, the MB Audit is an amazing test suite. It goes through really sort of every aspect of every possible combination of things that can be set within the 6522 interface chips and so on. We were seeing that even with all of these things behaving exactly the way that they should, we still were, we still weren't passing the test. And what we discovered was that there was actually some clock noise that was throwing off, everything related to not just the Mockingboard audio, but actually was probably impacting a bunch of other things as well. And so this was one that it was really good. Just for general reliability of the card that we, that we got in there, used the logic analyzer, looked at what was going on, and then basically put essentially, a clock noise filter on the incoming Phi 1 phase 1 clock that we use to drive most things on the card. To essentially make sure that we were filtering out, sort of erroneous clock transitions. And once we did that, then MB Audit passed. So this is one of those ones that was a serious pain in the ass. Took us a lot longer than we expected. As is most things with Apple II compatibility, there's sort of multiple points of failure that once you start digging in, ends up being ends up being a black pit of stuff. So a lot of folks helped out on this in terms of they giving us guidance and so on. But we're really happy to say that not only is it fixed, but I actually do think it improves the audible fidelity of the final result. So this was pretty cool. And of course, the next couple of slides verify that again, this is us passing MB Audit, meaning that it's being found in the correct slots. And of course, that total replay indicates it's a Mockingboard without speech, which was one of the other annoyance points. Was that it was incorrectly flagging speech as being present when it's not. By the way, I mean, that is still one of our bucket list items, is to get speech working. Unfortunately, the particular audio chip that is in there has still does not have a proper Verilog implementation by anybody, or to the best of my knowledge, that anybody's done a decap of it. There's a previous version of that voice chip that's close enough that that it could sort of, that has been replicated in Verilog, that could be somewhat hacked to behave like the speech chip in the Mockingboard. And in fact, if you look at how MAME handles it, that's effectively they emulate the previous one, and I should have come prepared with actual part numbers, but I'm having a complete brain hiccup at the moment. It's I think it's the SC01, and then is the one that has been emulated, and then the one that has not can sort of be cobbled together from the previous generation one that has been emulated, both in Verilog and in C code. So at some point down the line, you will see that from us. Hopefully, I know there's a number of people who are working on it. One of the nice things about the open source code base of A2FPGA is that it lets us mix and match, and things that we do can get leveraged by other folks in the community and vice versa. There is a little bit of dialogue between us and other open source implementers and folks for example, in Mr. FPGA and other places. So voice, hopefully one of those things we'll get to.
Hey, Ed, just really quick, shameless plug. On the title slide, we actually include the GitHub repo for all of the open source bits, and we welcome contributions and pull requests from the community. In fact, that's actually how we've been making the card better, is either suggestions, issues, people using the code, and then there have been several contributors as well. So we would, thank you to all of you, and we would encourage future participation if you're wanting to get yourself into this. We've done everything possible to make it as easy as we can.
Or for that matter, if anybody is working on other FPGA projects, as I said, I know that I've collaborated on Mr. FPGA and others and shared code and so on, and so there's a lot of stuff in there that's reusable for other FPGA based Apple II stuff, and all that is licensed in a very permissive way that at least the code we write is all Apache licensed, so it can get reused. But we do use a lot of GPL code, which if you use, you need to. It's all marked as such, and you'll need to comply with GPL restrictions around that. So let's talk about the Ensoniq, because that's been one that has been a big deal for a lot of folks. So first thing I want to say is, when A2FPGA kicked off, Josh and I were Apple II and II+ people, right? And so I would say that that sort of we just like I guess probably most people, these are sort of, you start this with what were the computers that were when you were first exposed to Apple II, and so without getting too specific into things, in terms of ages and so on, because none of us are getting any younger. Generally, the period of time, for me within the Apple II universe was II+, IIe, and so GS was something that we became exposed to through the process of the cards, the first generation of the card. And I'll actually talk about this a little bit. The A2N20 that has been available for the last couple of years was actually about the fourth generation of the card. We had just been building these things. It had always been our goal to open these up to folks, but there was a Xilinx version that the first version that we made that used I think it was Xilinx Spartan 7. So that was like the A2S7 card. Xilinxes were just too expensive for that purpose. We then created the A2N9, which we were very far along on, and actually had shared a lot of cards. And in fact, I still have a box full of them that we shared with folks in the community that was using the Tang Nano 9K. What we found was that the HDMI output of the 9K was just not compatible with a lot of TV sets, and so we'd switched on to the 20K, which with the Tang Nano 20K, which gave us more stuff. And anyway, and I actually spent a little bit of time talking about this in more depth as to the abstraction model around the software. But this long and short of it is that really the last couple of years has been going all in on the GS and just learning about the GS and catching up on what's part of the GS, the whole GS feature set. It's fascinating, and I'm sure this is stuff that many of you have live and breathe, but it's been fun sort of getting to learn all these pieces. And one of the things that was a big frustration point was what to do about the sound, the Ensoniq Dock 5503, which turned out to be a complicated beast. And we had actually had gotten pretty far along on, but just couldn't get the damn thing to work last year, ended up putting it on the shelf and revisiting it. And so the issues with the dock 5503, sort of, why is it so complicated? What was, go into a little bit of the history of how the chip was created, and it was actually designed by I believe the original sound designer for the Commodore audio chip, but it really approached the idea of going effectively being a sample player as opposed to sort of the previous generation of audio chips that were more about waveforms and sine waves and square waves and so on, and combining those with envelopes and mixers. The 5503 came to a different approach, which was to give you, and it was interesting to see how much time it changed in the space of a couple of years from those previous chips. They said, we're going to give you 32 oscillators, which is a very decent amount for, and this chip was the same one that was put in Sonic keyboards, which I actually do have one still in storage from the 80s. And what we're going to do is we're going to use a whole bunch of RAM, sound RAM, with these huge amount of oscillators that play back waveforms out of RAM, and that's how we're going to create an extremely versatile audio chip that is really capable. And so the GS ended up in a very uncharacteristic way for Apple at the time to go external, create this, license this chip, hook it up to the Apple II bus, the Apple II GS bus, which is already complicated, and there are plenty of great KansasFest videos that talk about things like the fast processor interface and Mega 2 and all of that I won't recap here. But in addition to that, they had to create a glue chip that interfaced this chip, this 5503, that was actually designed for a different type of processor, a 6809, with a different type of clocking mechanism, and interfacing that with the GS. There were some other issues around this that then made this difficult to implement in Verilog. The first thing is that, again, 32 oscillators, each of which has about 16 configuration settings, registers, effectively. You math that out and you end up with a whole bunch of registers. And typically within Verilog, you can have you can do your registers but typically you do that just as gates in your design. When you start to get to that many, it uses a whole bunch. So we did the naive design of this, and it was gigantic, and it actually just wouldn't pass any sort of timing. So then we said, okay, actually these registers need to be modeled as memory, which is good. Like the FPGA, the Goan FPGA that we use has enough memory in it, what's called block RAM, for doing this. But now you start to get into questions of how you access it, right? Because you've got to have your CPU, your Apple II, able to update these registers while you're continuous playing audio. And so that got into some hairy stuff. We did all that. We had a working design, but it still just wouldn't work. And that's where things sat for about 6 months. It was all in open source repo. People would periodically try to build it. They would go and say, this doesn't work. They'd send me some Slacks. I'd be like, I know it doesn't work. I'm going to get to it. I'd go and play with it a little bit. Then after a certain amount of time, got really ambitious and rewrote the whole thing. So it was much more efficient, and I was really happy with that. It tested very well in the simulator, but still just didn't work. And what happened was, it turned out that actually that glue chip that I mentioned that Apple made for interfacing the 5503 with the Apple II bus turns out to be actually really important, and there were some stupid bugs in it that were causing memory that was getting moved into the sound memory on the GS to come in with basically an off by one error. What this would result in is that most of the time the sound samples that were moved into the GS, because it was an off by one, the first byte wouldn't be set, it would be a 0. And without getting too much into the vagaries of how the DOC 5503 works, the 0 byte indicates stop playing the sample. So you'd go and listen to these things and you'd hear that like a bunch of the oscillators would not be playing, and you'd be like, okay, that doesn't sound right, what's going on? And so again, this was stupid stuff, but took months to figure out. And again, our bad on that. But just giving you a little bit of an insight as to why this stuff doesn't get often fixed as quickly as it could. As we went through this, lots of stuff. There's 3 different data sheets for the 5503. One, the original Ensoniq one produced by Apple, one produced at a certain point, and Ensoniq actually had sort of outsourced the manufacturing to another company. I think they might have been owned by the same thing. So you had 3 different data sheets with different levels of detail. You also had the stuff that's in the GS hardware reference manual and a bunch of other stuff. You also had a copy of the Apple Ensoniq trip report, which is a really good document. Somebody had sent that to me. I think it was Andre that do a shout out to that came from the Brutal Deluxe archives, but detailed a bunch of folks at Apple went to Ensoniq and went through a bunch of the things that still weren't working, and it shed a light on a bunch of stuff. The final part of it, of course, the audio. This with the 5503 is the first time that you had stereo and signed audio that was important. And so we're still dealing with some of the filtering issues. You'll hear that. We're going to play some samples for you in a minute. Audio samples. You will hear that noise, some of the filtering noise in the test run 2 intro piece. Most of the others sound really good, but we're still doing tuning on that. We do consider this an experimental release, but fairly easy to download and flash onto your device if you're really interested in playing with it. I know I went long on this one, but this was one that we've had a lot of questions on. So, Josh, how are we doing in queuing up the?
Yeah, we just need KansasFest team in the studio to queue up our video. Just really quick before you fire it up. Oh well, it's already rolling. Before you fire it up, this is experimental, but it is live on the GitHub repo. So if you want to play with it and you can build your own firmware following the instructions in the README, it is in the A2N20_enhanced board type of everything that's in the master repo. So this is live code. We're no smoke and mirrors here. And now we'll go ahead and roll the video.
One more point. Just one point. You actually don't have to do a build. There is and I'm not sure if the instructions make this clear, but there's a file stream that you will have to run OpenFPGA loader, but you don't actually have to.
That's right. No, you had left that behind for everyone. Yeah. So it's all out there is the point, and we would love for you to try it out. Let's roll the video.
cool. I think we're back live on that. So some hopefully good representative sound. We're still discovering a few different things. Some of it comes from the mixing, because a lot of what we found has been that a lot of the audio is designed for the mono mix, which, you know, most people at the time didn't have the stereo breakout cards, things like Light Sound or some of the others that did the stereo separation. So you see some games that, for example, only play on the left channel or things like that, and so that's interesting. And so we're dealing with that, and then some of it just has to do with the filtering and per channel audio volume that we're also still figuring out. So we expect that to get a little bit better. Really looking for folks to keep testing this stuff. Let me do a point of clarification on that. Actually, you know what? I think probably let me talk a little bit about how the card works. I think we just get into that on some of the next slides, because I'm seeing in the questions people are like, where does code run? We're talking about code. So there's a number of different approaches, and perfectly valid approaches. Look, it was discussed in the previous one. So the challenge of interfacing an Apple II to modern hardware has been solved and resolved many times over the years. Even with FPGAs. So you had the carte blanche card a bunch of years ago. That was a very cool card, very expensive to build, just in terms of the stuff that they used on it. There's been a lot of one-off video cards, things like VidHD's, very good card. I have one in my box of Apple II cards somewhere. Obviously, I use A2FPGA for those purposes now, but pretty cool approach. You have things like A2DVI, and you've got a bunch of interesting things. Some of those, they do fundamentally take different approaches. So one approach is to go and say, let me take a modern microcontroller, CPU-based thing like a Pi, tends to be the ones we see the most, and map that to the bus through various mechanisms. And the level of integration that you do with the bus really sort of determines what capabilities you can bring to bear. And a lot of this has to do with how many, as most people know, there's what is it, about 50 lines on the slot. They all do something, and depending on how many of those you can map in, you can do various things. For basic usage, for on a pre-GS and actually on a pre-2E, you can actually just with a very small number of lines, you can actually generate video out just by listening on off cycles to the video output stream. We actually did a very early version of A2FPGA that did just that. Do you want to do more complicated things? What you do is you typically listen to the full bus, and this is what most of the video cards do, including whether it's A2FPGA or any of these others. You listen to the bus, and what you do is you look for writes to the video memory segments. You copy those into a frame buffer that you're running within your device of choice, and then you generate your video off of that frame buffer. The mechanisms that you do that can vary within an FPGA, which is called a field programmable gate array. While you can run quote unquote code, as we would think about it, sequentially executed code, assembly, C, what have you. Typically, what you're doing is you're actually building gates, logic gates, that execute on this stuff. And what you do, and what folks like us did with A2FPGAs, we sit there and we study the Sather book, and we study all of this stuff and the work that's been done, and we create, hopefully, a fairly true fidelity recreation of what the chips on the device did. In some cases, you have to do things that are more CPU-like. So when we talk about where code runs, most of what we do is written in logic using a language called Verilog. There is actually some VHDL in there, and we use that. Some of the pieces actually do require a CPU, and that's where we talk about some of the things that are next. That's why I'm doing this setup. So within the A2N20, within the enhanced build of it, we actually do have a CPU code that runs, not for delivering any of the stuff that you saw here, but we're actually, and it's actually disabled in most builds, but what it does is it allows us to do a few things that you would want to do in code. And so one of them that is coming soon, we've been saying that for a while, but I think this time is really coming soon, is having an on-screen display so that you're able to do things like dynamically change card assignments. Right now we do a thing where we do new builds of it if you want a version that doesn't have Super Serial in a certain slot, or you don't want SuperSprite, or you don't want Mockingboard, or you want 2 instances of Mockingboard. Right now we do different builds around that. You will be able to eventually do that in an on-screen display dynamically. We have a menu system, works really well on the 2+2E. You can hold down the reset key. We give you the OSD and all of that. Doesn't work at all on the GS. I mean, it does work, but the GS obviously doesn't let you take over the ROM the same way that you can on previous generations, and so we're figuring that out. Other thing is disk access. We do have this also working, where, if you look very closely in the back of your A2N20, there is actually an SD card slot. It's hard to get to, but it's in there. And we do have prototype, and again, all this stuff is in the it's in the repo for the adventurous. You can actually boot off of a disk image on it. Right now, performance is not as fast as I would like to be. Mostly not from any. What we actually do is the Tang has enough memory on it that we actually pull the whole disk image into memory and run it effectively as a virtual RAM disk. But it's more just in our timing things within our disk to card implementation. So you'll see some stuff around disk access too. And so those are things you'll see within the current card. But other thing we did want to talk about is we actually are working with some later FPGAs, and I'm going to talk about some of those on the next couple of slides. So first thing I want to bore you with is kind of our architecture of how this stuff works and how this allows us to think about different cards. As I start off by going and saying the A2N20 that many of you have is actually the 5th generation of the card. We had previous versions, so if you look closely, it's A2N20 V2, which was the first ones that we let reactive go and sell to people. Prior to that, there was a V1 that didn't handle the GS as well as the N9s and the various versions before that that needed had other mechanisms. One of the things that lets us do this is that the code across all of these FPGAs is identical. There's this final piece that's called the bridge, A2 bus bridge, that is just an abstraction layer. It maps the physical lines that connect to the various things on the slot and the different level shifting approaches we've used into the rest of the code base. And this was generated by something called DeepWiki, which is a marvelous service that looks at your code and creates diagrams and so on. So anybody who's trying to learn the code, there's a DeepWiki link that does a better job of documenting our architecture than we possibly could have. Part of what this has done is what it lets us do is some of the different implementation details. So for example, this is the A2N20. This is the V2 version that uses a Xilinx part for the mappings of the pins. So what we did was we used a Xilinx part that did the level translation and mapping, basically turned all of the pins that you've got, the 50-something pins that are in that physical slot, into, in the case of the Tang Nano 20K, there were only about 18 usable pins once you got down to it that we could actually use. And so you see that in this slide on the right. That is the footprint of that Tang Nano 20K. Reality is we never loved that approach. In the intervening time, since we started, a couple of things. One is this is no longer an actively produced part, this Xilinx, and one of the A2FPGA principles is we've said there's been lots of great cards over the years that keep going out of manufacturing because they weren't using off-the-shelf parts. So the next version of the card actually drops back into using 74 series chips for the most part, and all active production chips. The result of this is a couple of things. One is that Xilinx part has been getting more and more expensive, and tariffs have not helped. So what was like a $15 part, and everybody goes and says, "Oh, Ed, I found on eBay, or I found whatever." That's great, but the reality is it's a phased out part that's not available from multiple distributors at any when availability varies throughout the year depending on whether you have like automotive manufacturers and restocking. So we've moved to essentially off-the-shelf parts, and this is what you see on this schematic that map the boards to inputs, and eventually, and what we'll do is we'll actually move to a more capable FPGA along the way. And so this is a design you'll see from us later this year. We're doing that thing at the risk of people going and saying, "Oh my God, I'm going to wait for that." Feel free to wait for it. We're not sure when it'll happen. What we also say is, unfortunately, the tariff thing has made all the costs crazy, even with the drop-down reduced tariffs. Part of what we're doing on this is because we're trying to reduce the manufacturing costs, because when you combine that with the fact that the assembly costs and such end up having 45% on top of it, we want to try to sort of address these things. We'll see what happens. But what that will let us do is bring a lot more capabilities to the table, and that's what you're seeing here is a prototype. This is actually working hardware that we have working in the labs. We're using actually a simultaneously more powerful and cheaper Tang Nano. So that Tang 25K is actually much more powerful, and that little board is about half the cost of what Tang Nano 20Ks currently sell for. At the same time, we're actually breaking out a lot of the connectors so that they're easier to get to, SD cards, USB host for being able to connect mice to it, the USB-C for connecting back to your host computer, and then HDMI, and then up at the top, that is in fact an ESP32 S3 for having Wi-Fi connectivity. And so no pricing. It will be more expensive than current cards. That's the only thing we can say, and no timing around that. If we were actually a serious commercial venture, we would be not showing any of these things until we have some of that in mind. But compatible with all the same code bases, all of the same features, and something that we hope to have available later this year. We're doing other stuff from a new hardware standpoint as well, specifically targeting the GS. Stay tuned for that. Other than to say that the code name for that is the Excelsior class, and I'll let Star Trek fans read into that as they may.
Yes, we refer to this one that you're looking at on the screen as the Enterprise 1701A.
Yeah.
This is our refit. By the way, just really quick, all kidding about Star Trek aside, the form factor of the board is only slightly larger than the current A2N20. Very slight modifications horizontally on the board plane. The other thing to note is that by using the Tang 25K module, we get rid of any potential overhang on the right-hand side of the card. So one of the chief criticisms that we've heard a few times is the Tang module has to sit inside some headers on the current A2N20. So you just have to be careful with your cable routing and so on and so forth. But this one eliminates that problem.
Very, very slim card.
Yeah, Ed's showing it to you right now there physically.
Yeah. So you see, like, you're not going to have the issues where you had other cards, abutted to it. It's just very flat and
surface mount.
Yeah, exactly. Cool. So I think we covered most of that stuff. I think that brings us to wrap up. So I don't know how long we went, or where we are in terms of remaining time. But if we do have time for questions, happy to jump into them.
Ed, there was one that was outstanding in the Discord. Did we write our own? Did we use GoWin IP for DVI, or did we write our own code for HDMI?
Oh, okay, good. We do not use GoWin code for DVI. What we use is something called HDL util /HDMI. By the way, all these credits are in the README. Most of the folks in the retro scene are using HDL util HDMI. The GoWin stuff is not bad, but it doesn't do the audio mixing. So worth looking at. I'm not sure is, but yeah, that's so that's the one we're using. And again, it's the same one that you see things like Nest Tang and a bunch of others use. But it's written in a portable way that if we had to switch to a different one, we would too.
All righty. Thank you, gentlemen. We are a skosh over time, so I think there are some more comments and maybe some questions in the Discord. But thank you so much. That was super informative and really, really interesting.
Thank you all.
Thanks, everyone.